Okay. All right, so this is the summary video for Lecture 6, where we're going to be doing some more examples using rectangular coordinates.
So last time we did spherical, this time different coordinate system.
Right. And I'm just going to skip over this. What we're going to do is simplify the general differential equation. In rectangular coordinates, we're going to determine and apply the boundary conditions and see the concentration profile.
And so remember, this is, if you look at Lecture 5, exactly the same steps, different coordinate system. That's it.
Right. So the first example is a one-dimensional rectangular system. What we have here, this is liquid B, and up on top is a gas with A, and A is going to be diffusing into the liquid B. We know that at the surface, the concentration is Ca0. That's just given, so we don't have to worry about where that came from. And it's reacting. Let's see, it's somewhere. Yeah, it's reacting in here, and it's actually disappearing. It's being decomposed in there. And there is a depth del. The thickness of a film on top is del, so that at this point, the concentration is 0, and everything below it is 0.
So the gas with A in it is penetrating into the liquid, but only so far.
Because it's being degraded, it's reacting and being consumed. And so, before we get started, let's talk about the boundary conditions. We're going to look at the places where we have boundaries, places where boundary condition. We've got z equals 0, and we've got z equals del, these two boundary conditions. And so at z equals 0, it's given that the concentration is Ca0. And, I need to move it up, boundary condition 2, at z equals del, it's given that Ca is equal to 0.
I would say that when I was learning differential equations, this kind of thing, it took me a surprisingly long time to figure out why they were called boundary conditions. They usually happen at boundaries.
Yes.
Not always. Yes, the other day, Lecture 5, we saw that there's, the center of a symmetrical system is also sometimes a boundary condition. Sometimes
Right.
infinity is a boundary condition, but a lot of times boundary conditions are at boundaries.
So this is a boundary right here at the surface. This, of course, is not a boundary, but it's still a place where we know a boundary condition.
It's kind of conceptual boundary because, in a sense, if you trapped off the liquid at that point, you would still have everything about the system you were trying to model.
Right. You mean if there was a
the
boundary
zebra
here, the solution would be exactly the same. Okay. Moving on, what we're going to do, we're going to use, again, your favorite equation, the equation of continuity. And this is in rectangular coordinates.
So now we see x, y, z instead of theta.
Right.
Phi, phi. I always forget how to pronounce that Greek letter.
Phi.
Phi.
Okay, so we're going to make some assumptions here. The first one is that it's steady state. Steady state. And that means that this term is 0.
Yay!
The second one is that there's no bulk flow. And actually, at this point, you're pretty safe in making that assumption all the time. We'll discuss that after exam 1, but for now, there is no bulk flow. So all of these terms are gone.
So we end up basically with the same thing that we were doing yesterday in spherical coordinates.
Well, I have one more thing, and that is that the concentration is a function only of z.
And we have that actually provided to us.
Well, it's not provided, but if we look at this, it doesn't matter. We're going to assume that it doesn't make any difference if you're up against the wall here or against the wall here. It's all just going in the z direction.
Yep, and physically the way I envision that is if you had like a probe of some sort, it wouldn't matter where, left or right, you dipped it.
Oh yeah, that's a good way of looking at it. Just how deep it went.
Mm-hmm.
Okay, so since it's a function only of z, so then the derivative of 0 of x is 0 and the derivative of y is 0.
And that's how we end up with that conveniently simplified first equation right below it.
Right, right. And now she's giving us that our reaction rate is first order. And so she then plugged that into the equation and multiplied it by -1, which is how we came up with this equation.
So far, algebra.
Yeah, basically. All right. And now, if you put this equation in the form y double prime minus alpha squared, that's a squared, alpha squared y is equal to 0. So you're going to divide by minus dab and put it there. So that alpha, again, is alpha squared is just k1 over dab.
So we basically took a really ugly looking differential equation, partial differential equation even, and we turned it into calculus 1.
Differential equations. Yeah. Oh, and by the way, let me make a note here that she does have partial here, but it doesn't have to be a partial. You could change it to a d. These could be d's because it's only one. Z is the only variable that in which it's changing.
So basically making all this into single variable calculus.
Yes. Differential equations. Okay, so the general solution for this gives us this equation.
And honestly, that is the kind of thing that I look up in a table of integrals.
Yes, you would look that up.
I do not memorize that.
And let me just make it clear. It's this. So the square root is just for the k1 over d diffusivity, and then times z. And all of that is the argument for the cosh. And it's the same way with the cinch. The same thing.
Yeah, thanks. That's not necessarily visually clear.
Okay, and also on the exam 1 equation sheet, you have your choice in finding the solution for this this derivative. You can either use coshs or you can use exponentials. So she seems to prefer coshs and hyperbolic sine, hyperbolic cosine. So we'll go along with that. Here are the boundary conditions that we defined. And if you, let's start with this first one. If you plug in this first one at z equals 0, Ca equals Ca0. So 0 is equal to C1 cosh of 0 plus C2 sinh of 0. And if you look at these, cosh, I need more space, cosh is of x is equal to e to the x plus e to the minus x over 2. So if I plug in 0, so cosh of 0 is equal to e to the 0 plus e to the minus 0 over 2.
Anything to the 0th power is 1.
So 1 plus 1 over 2. So I get cosh of 0 is equal to 1.
Mm-hmm.
Okay, so this becomes 1. And sinh of 0, it's not taking it, sinh of 0 is equal to e to the x minus e to the minus x over 2. So that would be e to the 0 minus e to the 0, which makes that 0. So this one becomes 0. Whoops, I put the wrong thing here. This should be Ca0.
Yep.
Right. So, and here we get C1 is equal to Ca0, and that's how she got that.
Mm-hmm.
Okay. I don't have space here to plug in the second boundary condition.
But
to
I think
get
you can, work
C2.
backward, plug into the solution,
Mm-hmm.
and then use the trigonometric identity to get C2.
Right, there's nothing fancy about that. The only thing she used was that the hyperbolic tangent of x is equal to sinh x over cosh x. All right?
Sweet.
Okay, so then she puts it all together and gets this lovely equation, which if you've done that, you should pat yourself on your back for going through that terrific math and getting a great looking equation. If you want to know what it looks like, let's see, it's if you look at, if this is Z and if this is CA, then it's going to look something like this. Or if it depends upon what alpha is. If alpha is higher in value, it might look like that. Depends upon the value of alpha.
And if I'm also trying to visualize that in the column of liquid here, so here's the gas, and then here's the
Del.
yeah, where it goes to 0. So there's a lot, right? There's a lot here, which makes sense, and then it sort of fades out.
Exactly.
To nothing as you get down.
Exactly. And if it's reacting faster than, fast relative to the fusion, then it's going to look like you've drawn it. It's very high concentration up here, and it quickly goes to low concentration. So like this one here, I hope you can see what I'm...
Yeah.
This one here would be a high level of alpha. This one here, this one up here, is a low alpha, meaning that it's diffusing, it's reacting fairly slowly relative to the diffusion. So that's what that means. Okay, and I've forgotten what her question was. She wanted to know the diffusion, or she wants to know... So let's just... She wants to find the molar mass flux at the surface. Okay, I don't know if that was part of the question, but we're going to do that for fun. So the mass flux is just, if you recall, minus the diffusivity times the gradient. dCA dZ. I'm sorry, there's no space. So she took the derivative here, and it's very easy to do. The derivative of the cosh is just this term times sinh. So she took that out here, and it's times the sinh of the same thing. And it's the same way for the sinh. The derivative of the sinh is just this times the cosh, and then it becomes the cosh.
So it looks a little complicated if it's the first time you see that equation. If you step through where it comes from, you're just sort of gradually adding bits and pieces in from the differential equations and calculus and algebra that you've known how to do for quite a while now.
Yeah, and it looks impressive. You could impress your friends here. And then evaluate the derivative at z equals 0, because we want to know the molar flux at 0 at the surface. And so here, remember the sinh of 0 is 0, and the cosh of 0 is 1. And so she plugged that in and came up with this expression here. Okay, and then to find the flux, all she did was multiply. Let's see, there was a negative, which canceled this negative.
Mm-hmm.
So that negative's gone. She put in the diffusivity. And here's the expression for the gradient. And as she mentioned in class, that del should not be there.
Yeah, so I'm going to zoom in a little bit so that people looking at the video can see that equation more clearly. So that big term that you circled, that's the diffusivity.
Yeah, this is the gradient right here.
gradient. I'm going to label that because
Right. And so I just multiplied that by minus the diffusivity, and of course it got rid of that minus, and so there we have it. And this del does not belong there.
that's a typo.
Right. Which she mentioned in class too. Okay. Whoops.
Different lecture slide.
Okay, here's the second example that she did.
Are we doing this one?
Yeah, let's go ahead and do this one. Here's the second example that she did. This is, we have a biofilm here on this plate, and I guess we're spinning the plate to mix the fluid. So water's coming in here with the phenol as a contaminant at this particular concentration, and it's being treated by the biofilm, and so the concentration that's coming out has decreased. And of course, if this is the concentration coming out, then the concentration, since it's well mixed, has to be Ca0 in here as well. Which means that the concentration, if we look at a cross section of it here, this is just half of it. There's another biofilm on the other side, but we're not going to look at that one. So here's a cross section of it. And over here in the fluid is Ca0. But as she explains in coming slides, that we can assume that the concentration at that surface is also Ca0.
It's a boundary condition.
Exactly. So she has actually simplified this for us by telling us, and if I can go through where she did that, she told us the concentration in the bulk fluid phase over the biofilm is constant, so in time and in space.
We're
However,
assuming it's well mixed here.
yes. There's no resistance to convective mass transfer across the fluid boundary layer. Okay, and it's equally soluble in both. So what she's saying here is that the concentration at the surface is the same as the concentration in the water. Okay, and that's where we're going to get our first boundary condition at Z equals 0. The concentration is equal to Ca0.
And we're defining this rectangular coordinate over here for that the Z direction, and this is 0 and increasing values of Z until we get to
Del.
del.
Yes, she's using the same notation. So let's talk about what happens at our other boundary, Z equal del.
Literally boundary.
Literally boundary. And she makes a point of telling us it's an inert solid surface. So there's no mass flux into that surface because it's inert.
Mm-hmm.
Okay, which means if there's no mass flux, then the gradient has to be 0. So we know that dCA dZ at Z equal del is equal to 0.
Now the del as the variable for the depth here.
Mm-hmm.
I don't know if that's the widespread notation for biomedical.
You'll see that often.
Okay.
It's not uncommon, but she could have called it anything. All right. So let's see. What else does she give us? In the biofilm, there is a reaction going on, and this is the reaction, how you calculate the reaction rate. And I believe that later she tells us that it is, I'm sorry, I'm moving around and around. Yeah, that it's first order. Okay. So she simplified it for us within the example. And the reason it's first order is because we have very low concentrations of Ca, so that Ca is basically negligible relative to Ka. And I think people are fine with that. Yes, did you have a question?
So this is just a note I'm noticing on how I'm thinking through reading all of this, because, if I was looking at this problem, I'd look at the diagram and go, okay, this is fine. And then I would see multiple slides with lots and lots and lots of information, and it might be easy to get overwhelmed by this.
Yes, it
But
can.
what I'm seeing here is, so we've got the diagram, which helps us set up boundary conditions. We have this, and if I look at this, a lot of these things are sort of justifications for why is this a good approximation.
Mm-hmm. Yes.
Also, same here. These are justifications for why is this a good approximation, why is this close enough.
Right.
So I could actually sort of, skip that. It would be good to think about in terms of when you go out into the real world and you're modeling systems that are really complex, about how you take assumptions like these and decide which simplifications you can make to get math like that. But that's what it is. Like, these explanations are all basically saying this equation is fine for our purposes. Right. Similarly here, like, a lot of this is basically this is fine.
That's right.
So this is mostly what you need to get from this slide is here it is, but here's how we got there.
Right.
And okay, here's some setup variables.
Yeah. So this is actually the problem statement here. We're going to treat 0.1 cubic meter per hour of wastewater, and we're assuming that we put 0.1 cubic meter in, we're going to take 1.1 cubic meter per hour out, because the only thing that's happened is we're losing a little bit of phenol, so the volumetric flow rate's not changing. It's flowing in at that concentration. Here's what del is, 2 millimeters.
Cool. I was wondering about where we'd find that.
Let's see, and we want to know what is the surface area of the biofilm necessary for us to achieve an outlet concentration of 0.02. So we've gone from 0.1 to 0.02.
And I'd also, bit of a side step here, but also noting that, right, these slides with all the here's how we're making this assumption, why we're making this assumption, depending on the system and depending on how precise we need it to be. If I did like a first rough approximation mathematical model like we're about to do now, and then went, okay, that's fine, but I'd like something with more detail. I think the subtleties are important here. Then I would go back to, this slide, that slide, and go, okay, I've made these massive simplifying assumptions. Which ones might I want to make more complicated?
Expand upon, yeah.
But right now we're doing kind of a back of the envelope thing.
This is beeping. Yeah.
Oop. Yeah, okay. We're trying to set a timer to see if we can get ourselves to be more concise.
All right, and she gives us some information here as well, which we're going to use. The question here is, so what surface area do we need? So what we need to figure out is at what rate is the phenol degraded, and that's just input minus output here. So here is the rate that phenol is degraded at. This is the inlet volumetric flow rate. This is the outlet volumetric flow rate, and they're actually basically the same. Here's the inlet concentration and outlet concentration. We're given that, so we plug it all in, and this is the rate that we have to degrade the phenol. Okay, this rate is also, we can also relate it to the surface area times the molar flux. So here's the surface area, and this is our molar flux at the surface of the film.
And we skip that by the definition of what the molar flux is.
Right. So what we want is the surface area. Okay, so we know what this is. We know what the diffusivity is. We just need to find what is the gradient at the surface.
Mm-hmm. And reminder of where we got that from. It's up here. And
That's
this was
given in a previous slide.
Your handwriting's much better than mine.
Mine is suffering as well. Okay, so here we are. We've got the reaction rate, and she took a moment here to calculate what K1 was. So we have that. And we're ready to now find the concentration profile. To do that, she kind of skipped a step here. She went back to that wonderful slide with all of those partial differential equations, took the one for rectangular coordinates. We made the assumption of steady state, no bulk flow, and also that CA is a function of, what is our coordinate? Only Z.
And that's what let us do all that lovely crossing out of terms.
Right, to give us this.
Mm-hmm. So you've seen that process a couple times by now. You should be used to it.
And in the exact same way, the general form of the solution is hyperbolic cosine and sine. All right, so now the only thing left is for us to find these constants using our boundary conditions, which we set up previously, and she's got the same ones here.
Yep, so this process is something we've done, like, what, 4 times now?
Yes. Okay, now the complicated part is when she substituted these in, and she didn't go through the detail here, but you get this equation for the concentration as a function of Z. And we've already gone over our 20 minutes time, so I'm not going to do this, but what I will do is write this down in notes, and we will post this separately. So you can see how she went from this, using the boundary conditions, to this. Okay, so I'll post that. And then remember, oops, trying to go too fast. Remember, what we need is the gradient. So she took the gradient, and I'll include this in the notes as to how she did that. Then she calculated what she called the Thiele modulus, which is just a ratio of the reaction to diffusion. And so the reason she's calculating that is because it's showing up here. So she's just calculating that in order to plug it into this equation. And so she found that it's 19.49, and with no units. And by the way, since it's much greater than 1, the rate of reaction is very rapid compared to diffusion. So you plug all of those numbers in, make sure all of your units work out.
That is an important thing. If you are working through and you've got some strange units going on, you probably skipped a step.
Yes, so I don't think this goes in here. I think that's the typo carried forward. And then you end up with, let's see.
So basically this goes into a calculator.
But you check your units.
You check your units and then you put it in a calculator.
And then plug it into the equation that we originally had to find what is the surface area. And it's right there.
So again, notes will happen to walk through this in more detail, but I think hopefully you're getting the idea of the process of boundary conditions from looking at the geometry, and then from assumptions about, steady state, no bulk flow, etc., how many terms can we get rid of?
Yes, the important part here, of course, is setting it up, understanding the problem, setting it up, and setting the boundary conditions. All the rest is math. And she didn't go through this, so I guess we'll stop here.
Yep. And I think
Okay.
we just go down to the bottom with the summary of topic just to...
We're making people dizzy. Okay. So what we did is we solved differential equations. In the rectangular coordinates, we identified and applied the boundary conditions and found the concentration profile.
Cool. All right, so we've done this with spherical coordinates and then rectangular coordinates just now. And I wonder what's next. Stay tuned for lecture 7.